This is just an additional video for solving exponential and logarithmic equations. It seems to be a topic that people struggle with a little bit, so I just wanted to give you a few examples and maybe help you think about it a different way. So the first way we're going to think about this is think of it as a function machine. So you have a function machine that's running forward, you're taking log base b of x. If you were going to take that machine and run it in reverse, so go the other way, it would be b to the x power, right? So it's just the inverse, and that's what an inverse is. What's done in one is undone in the other. So if you realize you made a terrible mistake, you can flip this lever on the side and it's going to undo whatever you just put through, right? It's two-sided. It doesn't matter which way you start with, but one way runs the log and the other way runs the exponential. Same thing could be said if you had, instead of log here, let's say you had x to the third power. Over here you would have the cube root of x, right? They're inverses of each other, so just flip it, and what's done in one is undone in the other. It's a machine that runs both ways. So I'm going to do an example of an exponential function to start, just because those seem to be easier for people for whatever reason. We'll just get one of those out of the way. So first thing I need to do is isolate this piece right here. But this is exponential function, meaning my variable is stuck in the exponent. So in order to isolate this, I need to add 14 on both sides. And I end up with 3 times e to the x minus 4 is equal to 27 plus 14, which is 41. Okay, I divide both sides by 3, and I'm going to leave this as 41 over 3. I'm not going to try and simplify it. And so what happens is this right here cancels out. I get e to the x minus 4 is equal to 41 over 3. Okay, I've isolated my base of my exponential piece, but I haven't taken the variable out of the exponent. So in order for that to happen, I need to use, we just talked about this, if it's an exponential function, the inverse is a logarithmic function with the same base. So the base of my exponent here is e, so I'm going to use a log with a base of e to eliminate that exponential piece. Log base e is the same thing as using ln. Okay, this is another idea though that people seem to get tripped up on. They say, well, I'm going to multiply both sides by ln. No, ln does not have a value. You can't multiply by ln. What you can do is apply the function of ln to both sides. And in doing so, the ln and the e to the power of something will cancel each other out because they're inverses of each other. What you did in one is undone in the other. It's like it never happened, right? If you ran something through that function machine, realized it was a horrible mistake, and pressed reverse, you would get back what you started with, right? It would undo what was done in one. So what I need to do here is apply ln to both sides. So really, what I'm really doing is putting this entire thing inside the function ln. And over here, I put 41 over 3 inside the function ln. I can't just multiply by ln. There is no such thing. If you put ln into your calculator and press enter without inputting a value, nothing happens, right? If you have a function machine called the natural log, ln, and you don't put anything in the top of it or in the input, even if that bar is running through, nothing's going to happen because nothing's coming out. You didn't put anything in. All right, on this side, I end up with these canceling out. I'm just left with x minus 4 is equal to ln of 41 over 3. I need to add 4 to both sides. Let me make this fit here. I add 4 to both sides to isolate x. And my final answer, once I put it in the calculator, I want to give it to, let's say they ask it for to the nearest thousandth. I enter 41 divided by 3 inside the natural log, press enter, and then press 4, and I end up with 6.615. So my final answer here, 6.615. Technically, I could go back and check. I could take x, plug it back in. I won't get exactly 27 because I rounded. However, if I took that value, did minus 4, then raised it as a power of e, subtracted or times 3, subtracted 14, I should get 27. This is a check here, just plug and chug. All right, so let's look at a logarithmic one. Before we do that, we need to check over here at our log properties, because if we're talking about two separate logs, I'm going to have to condense them before I can solve. So these are your log properties. The first one is the product. Two separate logs with the same base being added, I can combine as multiplied. Being subtracted, I can combine as divided, and with the coefficient, I can make it as an exponent. So if you need to review your log properties, that's 4.3, and there's also a video that goes along with that. So let's look at this first example, where I have log base 3 of 2 minus log base 3 of x minus 4 is equal to 2. What I notice here is that these two logs, they need to be combined into one log before I can simplify any further. And these two logs are being subtracted so I can use the quotient property and combine these as one log with a base of 3 with their insides being divided. So now I have log base 3 of 2 over x minus 4 is equal to 2. I'm trying to get the variable out of the log. So the opposite of logarithmic function, the inverse of logarithmic function, is an exponential function. However, not all exponential functions are the same. Just bear with me for a second, don't write this down. If I had something square root, to undo that I would need to square it. But if I had something that was a cube root, to undo it I would need to cube it. Same thing happens here. If it's a log base 3, then I need to raise both sides as powers of 3 in order for that to cross out. So these are both exponents now. The entire equation on the left becomes an exponent of 3. The entire equation on the right becomes an exponent of 3. In this case, these cancel. I'm just left with 2 over x minus 4 is equal to 3 squared, which is 9. I'm going to put it over 1 and cross multiply because my goal still here is to isolate x. I end up with 9x minus 36 is equal to 2. I add the 36 on both sides and get 9x is equal to 38, and x is equal to 38 over 9. I could simplify it. I could make that an improper fraction, or a mixed number, I'm sorry, but I'm going to leave it as an improper fraction. It doesn't matter to me. Again, I could plug this back in and see if it works out. What I want to be careful of here, keep in mind the domain of logarithmic functions is that x is greater than 0. So if I ended up with 0, once I plug this in either of my logs, or a negative number, I would need to reject that solution because the domain of x is greater than 0. Let's look at another example. If log base 2 of x plus 2 plus log base 2 of x is equal to 4, since this is two logs being added, I can actually combine these logs and multiply their insides. So this is really log base 2 of x plus 2 times x is equal to 4. Notice I didn't do anything to the right side yet because basically I'm just combining like terms. But since I'm using logs, there are special properties for combining like terms here. So I end up with log base 2, this is really x squared plus 2x is equal to 4. And I need to use 2 as a base on my exponent here because it's log base 2. So I raise both sides as powers of 2. I get 2 to the log base 2 of x squared plus 2x is equal to 2 to the 4th power. And I'm going to simplify here. On the left side, the 2 and the log base 2 cancel. I get x squared plus 2x is equal to 16. Move the 16 to the other side. And now I'm looking at a quadratic, so I need to say to myself, I have three options. I can factor, I can complete the square, I can use the quadratic formula. Just by looking, I'm saying factors of 16 that subtract to give me 2. Well, my options are 1 and 16, 2 and 8, 4 and 4. None of those work. So you know what? Instead of completing the square, way more work, I'm just going to do quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I plug in all of my pieces. Careful with your signs. And I'm just going to go right to the calculator now that I have these. So I do the square negative 2 plus the square root of 68 and then divide it by 2. And I get that x is equal to, I should have two answers here, 3.123, and x is equal to negative 2 minus the square root of 68 divided by 2. And I get negative 5.123. But keep in mind, what did we just say? We want to make sure that there's not a negative inside of a log because the domain for our logarithmic functions is that x is greater than 0. Therefore, even though I have these two solutions, if I was to take this solution and plug it back in, it's going to give me a negative in both of the logs. So I actually need to reject this. So I reject because domain x is greater than 0. So my final answer is just this one. Okay, here's another example you can try on your own. If you'd like, it's 3 times ln of x minus 2 plus 15 is equal to 35. First thing you want to do here is isolate the ln, and then I'm not going to do this one for you. There's no log properties that need to be applied here, but if you want to try it, it's a good example. If you are going to try it, though, I will give you the answers just so you can see if you're right. In the end, you should end up with x is equal to 787.772. So again, think of a logarithmic and exponential function as a function machine in which one direction is the log and the other direction is the exponential function. What's done in one must be undone in the other, and all our same rules of equations apply. So if I'm applying it to one side, I need to apply it to the other. And again, we don't multiply by a log, we don't multiply by ln. We raise things to powers, or we apply the log, because it's not a value, it's a function. So keep in mind all your rules of functions, and something that would also be helpful to review would be your proper